The concluding part of our lecture is kind of a fun one. It's what I like to call capacitor games. And it's kind of like little puzzles in which you change something about a capacitor, like the material or the dimension, and you got to predict how various quantities, for example, the capacitance, the charge, or the voltage difference, the electric field, or the stored energy, how those would change. And you got to be very careful because there's some little tricks that actually may be non-intuitive. So let's start with the things that you can count on. So some of these games say, you charge the capacitor and you disconnect the battery, and some of them say you leave the battery connected. Different things happen when you do those two things. For example, if a battery remains connected to a single capacitor and you're not adding any other capacitors in series or parallel, then one thing has to remain constant. What must remain constant if you have a battery and it stays connected to it? Hint, a battery is typically like this one. Oh, it says 1.5 volts. So if your battery stays connected, that means that delta V must stay constant. If your battery stays connected, delta V will not change. It'll just be the delta V across the battery. Now, how about this? If the capacitor is charged or, in fact, discharged, then entirely disconnected from the battery. So, in other words, like we hook this up to our battery, like this, for example, I can hook it up with my light here, and yes, it will, even while I'm doing this, it will light up because the charge is flowing. So I'm charging my capacitor, and then what I do is I disconnect it. There it is. What must stay the same no matter what I do to this capacitor? Well, if it's disconnected from the battery, that charge is stranded on there. So the Q must remain constant. And these are the first two clues that you have to use. If the battery remains connected, delta V is constant. If it's disconnected from the battery and there's no way for the charge to get off, Q must remain constant. Other than that, the relationships you got to use are that C equals Q over delta V. And you also have to use very often mostly we play these games with parallel plates. The capacitance of a parallel plate capacitor is equal to kappa times epsilon naught times A over D. And this includes the fact that if you have a dielectric in there, so there's one relationship that you use. There's another relationship you'll very often use. Also, delta V is ed. Again, we do not use, you don't need to use negative ed because in capacitors, the signs don't matter. There is yet another thing. For a capacitor, the UC of the capacitor is 1/2 Q delta V, which is also equal to 1/2 Q squared over C, which is equal to 1/2, whoops, ran out of room there. The last one is, it's also, I'll put it right over here, 1/2 C delta V squared. All those things, these are also useful things to help you through these capacitor games. So let's go ahead and play, and you guys can see how it's done. Actually, we've got two games to play. An air-filled capacitor is connected to a battery. Now, when you see air-filled, basically that just means kappa is equal to 1, 1.0005 something, but you can just forget about it. It's basically equal to 1. And then it's disconnected. Do the following quantities increase, decrease, or stay the same when the plates are pulled farther apart? Plates pulled farther apart. So let's just model this. And remember that here's our plates like this. They're close together. Our charges, if the plates are close together, are very happy. They're right next to their oppositely charged buddies. But when you pull it farther apart, it's not as stable. It's, in fact, I've got to do work. I've got to pull these, got to exert force to pull these apart. That gives the whole system greater potential energy. And if it has greater potential energy, it's not as stable. What happens to C? Well, notice that C is equal to epsilon naught. I'm not using kappa because it's just a 1. A over D. Well, as D increases, because we're pulling them farther apart, capacitance goes down. And that'll give us clues for the rest of this stuff too. What happens to Q? It's disconnected, so what happens to Q? It's got to stay the same. What happens to delta V? Well, here's where our capacitor equation can come in handy. We know that since caps are quite overvalued, we know that the capacitance is doing what? It's going down. The charge is staying the same. What does delta V have to do? Delta V must go up for that to be true. Delta V goes up. Now, what's going on with that? Why is delta V going up? I kind of gave you a hint before. When you pull these two things apart, the field strength, well, we'll come to that, but I'm actually pulling them farther apart. So it's just like pulling them up a hill. The electric potential difference gets greater. They're farther apart. They've got more potential energy per unit charge. So the delta V actually goes up. And that actually requires work for me to do that. What happens to the field strength? Well, you might say, oh, delta V is Ed. Oh, well, and delta V is going up, so E must go up. Oh, we can't do that because D is also going up. As it turns out, the electric field, and we can just do this. I can just draw you a picture for this so you can see this. When we go like this and draw our capacitor, I'll put 4 charges on there. Minus, 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 minus. Here are my field lines. And the field lines do represent the strength of that electric field. What happens when I keep Q the same, but I pull them farther apart? Look what happens to the field lines. Are the field lines getting any closer or farther from each other? Yeah, they're longer, but look at the field line density in here. They're this close together, they're this close together. E is constant. The electric field does not change because E is just equal to sigma over epsilon naught. Notice that sigma has not changed. This stays the same. Why? Because the Q stays the same and the area stays the same, so sigma stays the same. Finally, the last thing is potential energy. Well, because U equals, which version of this can we do that is unmistakable so we know what it is? I'm just going to use this. 1/2 Q delta V. We see that delta V goes up, Q stays the same, so this goes up. U increases. Cool, we won the game. Let's play another version of that. In this time, you might say, wait a second, this is the same thing. We got an air-filled capacitor. It's connected to a battery. Do the following quantities increase, decrease, or stay the same when the plates are pulled farther apart? You may say, wait, we just did that. We did not. Because what is the difference? Notice that in our first game, the battery was disconnected. That is not the case here. The battery stays connected. So which one can we instantly do that we know stays the same? If the battery stays connected, and here it says right on here, 1.5 volts, this battery is not changing. That means this is going to stay the same. Let's start with capacitance. What will capacitance do? Well, by the same logic, if we increase the distance between the plates, it goes down. What happens to charge? You may say, oh, it's probably the same as last time, it stays the same. It does not. As we pull these farther apart, we've got the constant delta V. As we pull it farther apart, the capacitance gets weaker and weaker and weaker. It gets to be a worse and worse capacitor. So the same delta V will hold less charge on there. Let's just show it mathematically. Caps are quite overvalued. This stays the same. This goes down, it decreases, so Q must go down. The charge decreases. What happens is charge retreats, like in this drawing right here, the charge retreats back to the battery. it'll actually leave the plates and go back to the battery on both sides. So charge will decrease. What happens to the electric field? Well, by the same logic as last time, if this is sigma over epsilon naught, and this is Q over A over epsilon naught, notice that that will also decrease. There's fewer charges. So it's like the difference between this, I'll draw our new one. Once some of these charges leave, let's say we only have that much charge on it. Notice that my field lines are less dense than I had over here. Compare this with this. Field is weaker, much weaker. Electric potential energy of our capacitor? Well, we have its same concept there, 1/2 Q delta V. The Q this time changes, it gets lower. Delta V stays the same, so this lowers, U gets lower. So you can see how to play the games, and there's plenty other versions of the game to play and have fun. So enjoy this chapter. It's relatively easy. Nothing in AP Physics is easy, but this is, compared to a lot of stuff we've done, this is one of the more fun and easy ones, and it's so useful.